My name is Anirudh. I'm here representing Twitter. And today I was going to talk about analytics framework that I, along with a couple of other people at Twitter, have built out. We call the framework SAR. It stands for the words a time series aggregator. And I wanted to try and go through the motivations behind why we built it out, some of the challenges that we faced, and the solution that we came up with to solve those problems. Let's dive into it. So first question, what is SAR? So SAR is a framework and a service infrastructure for deploying time series aggregation jobs. So for some context, Twitter has a very broad need for time series aggregations. What I mean by that is if you are a publisher, say BuzzFeed or New York Times or any other publisher, you post content onto the Twitter platform. And you typically want some sort of feedback loop as to how that content is performing. So you want to measure how many people have viewed your tweets. And you want to track that month over month or week over week or day over day. You want to track the number of favorites, retweets, replies that you have received. So you want to track engagement of content on the Twitter platform. And you want to aggregate on that and then display it as a time series dashboard that publishers can use. Time series aggregation jobs are very common even internally within Twitter itself. So if you think about it, we have an API that's used by millions of developers around the world. We typically want to know how that API is being used, which endpoints are being hit the most number of times, what is the total number of requests that are being made, which client application ID is making that request to that endpoint. And this gives us internally within Twitter some insight into how our API is performing. What are the most popular endpoints? And we can then track that and measure that over time. It also allows us to catch spammers. If a spammy app is hitting a particular endpoint too many times, we can track that as well. And then there's a third aspect to that, which is site health, for example. So we want to measure observability as to how our services are performing over time. How many success metrics do we have? Failure metrics do we have? And we want to track that over time so we can calculate for how long our platform was up. So in short, time series aggregation jobs are a very, very common problem at Twitter. They aren't a complete totality of all the analytics problems that Twitter needs to solve. But our course of our team's experience has been that they account for a huge chunk of the problems. And so we built a framework specifically dedicated for these type of problems. And this framework has been in production at Twitter for maybe about a year to a year and a half at this point. And we've reaped many, many benefits from having a managed framework for this. What I mean by the managed framework part is that before we built out the SAR framework itself, a lot of these, Twitter was still doing analytics dashboards. We were still providing them to advertisers a while back. But it was being done in a very ad hoc manner. People were cargo culting some scripts, some Hadoop jobs, building out some custom pipeline that was not managed. It was not very robust. It would break very often. It was harder to evolve. And we built out a service infrastructure, a managed framework that allows you to solve all of these problems in a very robust manner. So given that, as I talked about here, it's a very common problem at Twitter. It's used for data products like engagements, which we provide to external advertisers and publishers. It's used for business metrics like measuring how our API is performing, for measuring site traffic and user engagement. So time series aggregations are a common problem. And as I mentioned, this is a very common problem, and it's very hard to do this problem at scale. Twitter receives billions of events per day, and we want to compute and aggregate on these events in real time and produce and then evolve on this schema as we modify our job and as new requirements keep coming up. So, as I said, one of the main things is that our course of our team, Twitter was doing this long before, and this has been a multi-year effort at Twitter to come up with a robust solution that does this in a general way. One of the first few things that Twitter developed was a framework called Scalding, which essentially, if some of you guys I don't know how many of you guys are familiar with Scalding, but if you guys are familiar with other MapReduce frameworks like Pig or Hive, Scalding is a MapReduce abstraction library that's built over Hadoop, over MapReduce, but written inside Scala. We developed that in-house at Twitter, and then that's been open sourced and can be accessed. We also developed a technology called Storm, which is a streaming compute platform that can process events in real time and aggregate on that. And then we developed another technology in-house at Twitter, which is kind of what the core of SAR is built on, which is a technology called Hummingbird. Hummingbird is a technology that's built at Twitter. It's been open source, so you can access it today on GitHub if you want. And the whole point of Hummingbird is that you write a Hummingbird job once, and then that job gets translated into a scalding job, which runs in batch and computes your data in batch mode. And it also gets translated into like a Storm platform, and that computes your data in real time. And then you combine the results of the batch and the real time to provide the combined results, the merged results back to the client. So Hummingbird is a framework that was developed at Twitter. So as we can see, like Twitter had first developed Scalding, then we had Storm, then we had Hummingbird. Hummingbird provides a very, very good computational framework for allowing you to specify the business logic of your job. However, our experience was that just specifying the business logic, there is a lot more to it. There is an entire service infrastructure that needs to be built on how to evolve your job, how to manage things like backfills. For example, if there's a bug in your deployed job, how do you correct that data? And Hummingbird doesn't provide the tooling for those kind of things, and that's where SAR comes in. So SAR is an end-to-end service infrastructure that's built on top of Hummingbird. To further drive some of the motivations in a more concrete sense, for example, if the business team at Twitter wants to know how our API is being used, they want to measure every single API call that's being used, and they want to bucket it. They want to bucket it by a variety of dimensions. This could be the API endpoint that's being used, the data center that is being hit, the client that is being used, etc. You want to then compute several metrics on this. So you're aggregating on some dimension, and you want to compute some metrics. These metrics can vary. They can be, give me the total count of requests that were made to this endpoint. It can give me the total number of unique requests that were made to this by a particular client application ID or by a particular user ID. It can give me the mean response time. So there are various metrics that you compute on some dimension that you are aggregating on. And then you might want to write this data out to a relational database. Like I've taken Vertica as an example here because it's something that we use pretty often internally at Twitter. But you can write it out to say MySQL. And the usefulness of this is that you can then like easily explore this data. Like you can run SQL queries on these aggregates. And then you can like figure out, and you can come up with some useful analysis from it. Another example could be for a product-facing product would be like impressions by tweet. So we have about 500 million tweets that flow through the Twitter platform every single day. However, 500 million tweets is a very big number. However, the number of impressions, that is the number of views that each tweet receives, is many, many orders of magnitude more than the number of tweets. So we want to compute, or we want to show, if we want to show in our product, how many impressions has every single tweet received, then you're aggregating on a particular dimension again here. You're aggregating on the tweet ID dimension. And what you're computing is the total count of the number of views that every single tweet has received. You're computing the number of unique users that have viewed that tweet. If it's a product-facing feature that's being surfaced in like your Twitter for iPhone application, you typically want it to be backed by a high SLA query service. You want it to have a high SLA and you want it to be robust. SLA is service level agreement. So it's like, how quickly, what is the agreement that like, if you specify that you have a 99.99% SLA, it means that all requests will be satisfied, like 99.99% of the requests will be satisfied for you. So in the old example, we used a data source like Vertica that we write the data to. For something like this, you might use a key value data store. So you might write the aggregates out to a key value data store and then expose it via a query service that then combines the results. But again, the logic is the same. You're aggregating on some dimension, and you're computing some metrics. What changes over here is the data store that you're writing your data to and the different SLAs that you're providing. A more complicated example would be like card analytics. So these are like engagements or dashboards that we show to external publishers like BuzzFeed, New York Times, etc. So you want to identify. So BuzzFeed wants to know how many people have tweeted links to their website, for example. Or if they have sent out a tweet, how many people have engaged with that? So again, you're computing the dimension here are tweet IDs or the URLs to links, which are the URLs to that publisher's website. The metrics that you're computing here can get complicated. They can be uniques, which is something we've talked about. They can be counts, which is again something we've talked about. You can also, SAR also supports like rankings. So you can say, give me the top tweets, the top 100 tweets that receive the most amount of engagement that pointed to BuzzFeed's website. And we can talk more about how we do counts and how we do uniques and rankings inside SAR. I'll get to that in the next few slides of my presentation. And then this again gets exposed via high SLA query service. And we can also write this to Vertica to also do some cross-validation. So that's kind of like some of the examples for why, the motivation behind why we actually ended up building out SAR. So before the SAR framework existed, Twitter was still doing these analytics. However, we were doing it in a very ad hoc manner. And there were many problems that came up with this. One of the biggest problems is service interruption. So real-time is hard to do, and at Twitter scale, it's even harder to do because you're processing billions and billions of events per day. What happens if your real-time aggregation service goes down for a while? How do you then recover your events? Do you simply lose data? Do you have a gap in your analytics dashboard saying, hey, BuzzFeed, we don't have data for this particular period? What is some solution that you come up with to make your service more robust? You have data schema coordination issues. So in some of the examples we've gone through, in some examples, we had data being written to Vertica. In some examples, we had data being written out to a key value data store. In some examples, you can imagine that aggregates are written back out to like a data store like HDFS. And then you have further downstream jobs that read these aggregates and do further processing on them. You might want to write your data out to a cache. So how do you coordinate? It becomes the sole responsibility of the programmer to figure out what data schema to use for what data store you want to write your data to for every single SAR job. And SAR kind of abstracts the details away. The user doesn't have to define a data model. SAR will take care of that. And since it's a framework, we can build best practices into it. So we build it out in the most efficient manner so the user doesn't have to worry about that. Typically, one of the next things that come up is you want schema changes. So you launch the first version of your product, and you receive some feedback from your users about it. And so now you want to evolve your product. You want to aggregate on some other dimension. Or you want to compute a new metric. Like previously, you were only computing counts, and now you want to compute rankings as well. So you have to go back in and change the business logic of your job. You have to furthermore change the data model, the data schema of the downstream sinks, like your key value data store, your Vertica, etc. And it becomes a very painful process because at every piece in your stack, you are making changes. And SAR abstracts that away. It makes schema changes extremely, extremely simple. And lastly, one of the most common problems is, and which is a problem that I honestly think is one of the biggest features of SAR, because it's very easily overlooked when people build a product out the first time, is inevitably you are going to make some bug in your job, and you're going to deploy that to production at some point. And that's going to mean that you are aggregating on some dimension in an incorrect manner, or you are computing some incorrect metrics. Then you realize this at some later point, and you now have to go back and correct your data. So this notion of backfilling or repairing old historical data is often overlooked when you first build your product. And our experience has been over like many years that this is a very common problem, and it's an extremely hard problem to retroactively solve if you haven't thought of it in the first place. So when we built out the SAR framework, backfills were made a first-class citizen inside the framework SAR. Backfills are not only useful to repair historical data, however, in the previous example where you evolve your schema, so your V1 product only did counts, your V2 product also does uniques. Now, you also want your uniques going back in time. So you again need to do a backfill. So when you evolve your schema, you want the evolved schema to also be there for the data that you had already aggregated on in the past. So backfills become useful for that as well. And these are all problems that we had to grapple with, and which also led us to develop the SAR framework. And most importantly, as we said, we wanted to solve these in a very general way. So every single job, every single user doesn't have to worry about this. It's solved once and for all, and then the programmer can just take advantage of these problems, of our solutions. Before I go on, any questions so far? I can stop right now. Yeah?
Do you set up your system architecture as a microservice with Scala and a environment? Or
yes. So every single SAR service, every single user who wants to develop a SAR job or aggregate a new log source, for example, would have their own SAR service. So you are isolated or sandboxed in that sense. Yes.
As a microservice or as a total package?
Could you clarify what you mean by microservice versus total package?
Like you want to have a system that has random walks that will be flexible when they're using a lot, you increase more capacity when they're decreasing your
We won't handle your capacity situation for you. Like that's like we can't generate machines for you automatically. Like that would be handled by something like Mesos or some other stream downstream like that. What we provide you is we provide all the tooling for you. So if you have the extra hardware, you can seamlessly do all of this. Essentially, that's what we would do. Okay, I'll move on to some of the basic SAR design principles that we incorporated. So the very first, probably the most important design principle, is this notion that we process every single event twice. So I talked about the Hummingbird framework, where the Hummingbird framework says you write your Hummingbird job once, and that gets translated into a scalding job and a storm job. Where your scalding job is essentially like a MapReduce job, which is running in batch mode. So that reads data from, say, typically from HDFS, and then processes the data, say, daily, and writes those aggregates back out to HDFS. You also have your events coming in real time into, say, Kestrel queues or Kafka queues, which you can then read in real time in Storm. And that event gets processed in real time as well. So you have both pipelines that are running concurrently. Your batch pipeline writing out data and your real-time pipeline writing out data as well. The advantage of this, and then after you have these both data sources that are writing data out to data schemas, you have a single query service that then reads the batch data as well as the real-time data and combines the results in a coherent way to give the most updated results back to the user. The way the query service ends up doing this is it favors the batch pipeline. So if a particular timestamp has data from the batch pipeline, we use the data from batch, because inherently the batch pipeline is going to be more fault tolerant, it's going to be more robust, and that's the advantage of the batch layer. However, if the data for the batch, like if the batch job has not caught up, because the batch job is running every 24 hours, so the data for the last, say, 24 hours is not going to be available in batch, it's going to be available only in real time. We take the real-time data from that particular part. And so this gives us the recency of real time as well. So we have the stability, the robustness, and the fault tolerance of the batch layer, as well as the recency of the real-time layer. And this is like the key feature of Hummingbird. And the way we can do this is we can combine both the batch and the real-time aggregates together via the query service, because the one limitation that we impose on the data model is that any single metric that you impose has to have a monoid structure. So it has to be commutative. So you can combine two things together. And this works actually pretty well. Like the next question that you might have is, if you impose that restriction, how do you compute something like uniques? Because uniques are computed via exact sets. Like you can't take a unique of 1 and unique of 2 and then combine them to get a unique value out. There are actually very, very good approximation algorithms out there. Something for uniques, there's an approximation algorithm called hyperloglog, where you can combine two. Hyperloglog gives you a monoid structure. So you can combine two hyperloglogs to get another hyperloglog that you can then derive at query time to get an actual unique value. And this is an approximation algorithm. So it can give you the exact unique answer within, say, a percentage of error that you can then calculate. So you can compute how much, what is the unique value that you want to give to like what precision and how much data, how much storage you want to use. Similarly, for rankings, there's a monoid structure which backs it called the sketch map that you can use for this thing. And you can combine two sketch maps to get another sketch map, which you can then derive to get a ranking out. That is to get like a map out. So, sorry, give me a second. So this architecture is called, like, typically what this term has been coined in like the big data space. It's been coined like a Lambda architecture, because you have like a Lambda, so you're computing it in batch and you're also computing in real time. So you have your batch layer, which is computing data from, say, HDFS, and your real-time layer that is computing data from your speed layer, which is computing data from like Kafka or Kestrel. They both write data out, and your query service combines the results and returns them back to the client. Okay, saw a question here. Yes, it's the same computation that's being done.
So how come you don't take what's coming out of the speed layer in Kafka and write that out to long-term storage instead of having to recompute it again?
Yes, the reason for that is that real-time is inherent. Like, what happens if your real-time aggregation service goes down for 10 minutes? You end up missing that data, right? However, your batch layer will end up coming around and will end up sweeping that gap out in your data and will automatically repair that data for you. Real-time inherently is more subject to failures. The batch layer is much, much more battle tested. You can control it a lot more, and it gives you much more fault-tolerant guarantees. So we always favor the batch result as a result. If you have the data being computed for the same time in batch and real time, you'll always favor the batch result. That's the reason. Yeah.
So why not save the real-time data on occasions when you didn't have an error?
How do you know if you had an error or not? Sure. So you still have the batch layer, right? But then you can't figure out that, oh, my real time had an interruption, so now I'm going to fire off a batch job to then compute that day's worth of data, because then that's going to require your batch job to actually start up again, and you're going to have to wait for your batch job to catch up again. Like that's going to add a lot more additional latency to your pipeline. In this way, it's being done in a structured manner, so you always end up favoring your batch layer in this sense. Yeah. Yes. Yes. Exactly. Yep.
So, I mean, how does the batch scale, though? I mean, the amount of data is growing. Isn't that batch process going to have to keep growing as well over time?
Your batch job just computes. For example, if your batch job is running on a daily cycle, Your batch job only computes that day's worth of data. It writes out, say your batch job started on August 1st. It writes out August 1st worth of aggregates into like a long-lived data store. Then it writes out August 2nd's worth of data. Then it writes out August 3rd's worth of data. And if your query is from August 1st to August 7th, it then takes the aggregates from August 1st, the aggregates from August 2nd, the aggregates from August 3rd, and then combine them at query time. So the amount of data that your batch job computes is actually constant over time. Yep.
How much extra time do you put on the real-time buffer? So if you do that,
it's up to you. It's configurable.
Do you have any recommendations, or what?
It's completely configurable for you. Yeah. Okay. I'm going to try and move on because I want to get to some of the talk. The second principle is that we wanted to separate event production from event aggregation. What I mean by that is there are two types of stages to any event aggregation technology. So the first step is you have your raw sources. So your API service that's like serving your API calls, writes out log data out to HDFS. You now need to read this raw source data, which is typically very, very large, and then transform it into some events that you can then aggregate on. So first step is you read these raw source events, raw log events, and convert them into some formatted event, some formatted, which typically we use thrift, some thrift struct event. And then the next step is that you then now aggregate on this on some dimension and produce some metrics. So the two steps is, one is you want to produce these events from raw logs, and the next step is of performing the event aggregation. The second step of performing event aggregation is common to every single SAR job. So it's common to whatever dimension you're aggregating on and some metrics that you're computing. That part gets abstracted away by the SAR framework. What's different for every single SAR job is what is the raw logs that you're reading and what is the event that you're producing. The second step becomes very mechanical, and so we abstract that away. It'll become clearer when I show an example in like a slide or two. The third thing is we have a unified data schema. So this, as I mentioned, like if you have a SAR job, you might want to write it to multiple data sources. You can write it to a cache. You can write it to a relational database like Vertica or MySQL. You might want to write it back out to HDFS for downstream aggregation jobs to pick up. You might want to write it out to like a key value data store. Now, if you have a user that wants to write it out to like data store 1 and 2, another user might want to write it out to 2 and 3. Another might want to write it out to only 4. Now, you have to define the data models for each of these schemas. You then have to set everything up so that your job computes aggregates and the key value structure that it writes out, or the relational database type of format that it writes out, is consistent and works for all of these things. And that puts this strain on the user itself. SAR abstracts away the data model schema for you. Also, when you evolve your job, so now when you evolve your schema and aggregate on a new schema dimension, we again evolve your schema for you automatically in the data store. So you don't have to change your schema at all inside. You don't have to go into your key value, into your Vertica database and add a new column into your Vertica database saying, hey, I was only aggregating on dimension A, now I also need to add a column for dimension B. We automatically do that for you as part of the SAR deploy process. And the fourth thing is we provide an integrated service toolkit. So there are many, many steps to a SAR job where you have to deploy some scalding jobs, that is Hadoop jobs. You have to deploy a real-time Storm job. You have to deploy a query service. You also want to deploy, if you have a production instance running at Twitter scale, you want to have alerts for your batch job, for your Storm job, and for your query service. You want to have observability into all of these mechanisms. You want to set up some sort of monitoring systems for data fidelity. Like in case some upstream source had some error in that, you want to be able to catch it. So you want some checks on data quality. You want to deploy those as well. So there are a lot of things that actually go into an analytics pipeline from scratch. Things like frameworks like Hummingbird provide you with a computational framework. However, it doesn't provide you with these kind of deployment tooling. And it doesn't provide you with the tooling that connects all of these together in a coherent way. You would have to build that yourself automatically. SAR tries to do that for you. And it tries to do all of these for you by a single deploy command. You like press like into your terminal like SAR deploy, where SAR is like this is written, the tool is written inside Python where you add different commands. So you do like SAR deploy batch and it'll deploy your batch job for you, or SAR deploy storm and it'll deploy your storm job for you, or SAR deploy query will deploy your query job for you. So these are all built into a SAR tool that we have written using Python, and it will deploy all of these separate components for you and deploy them in a coherent manner so they're all connected with each other. So I want to try and focus on a single SAR job, and let's try and motivate what the framework comes from. So the example that I wanted to focus on is a tweet impression. So what this job is trying to do is we have many, many tweets coming into Twitter. We have 500 million tweets per day. Each of these tweets receive tens of billions, so many orders of magnitude number of impressions on them, that is, number of views on these tweets. You want to aggregate on these in real time, and we want to produce a count, that is the total number of users which have seen every single tweet. And we want to write this out to some key value data store. A typical SAR job looks something like this. So this is a first example of what a SAR job looks like. This is written using a Scala DSL. So the SAR framework is managed basically by two programming languages, Python and Scala. So Python is where the SAR tool is built that provides the toolkit, and the Scala DSL is where you specify your dimensions that you're aggregating on and the metrics that you're computing. So if we try and walk through this example, the first part is this on keys. So the on keys is what are the dimensions that your job is aggregating on. So in this particular example, you are aggregating on the number of impressions that every single tweet has received. So your dimension is the tweet ID. That is, what is the tweet ID which I want to compute things on? You have the produce block, which says the metrics that I want to compute. So in this case, I want to compute counts. What is the count of the total number of views that every single tweet has received? So that's the metric that you want to compute. You have a sync to block, which is specifying what is the data store that you want to write data to. So Manhattan it's not New York, sorry. It's our internal key value data store, which is a key value data store that we write data out to. And the from producer block is your Hummingbird fragment. So if you notice, this Hummingbird fragment is reading from the client event source. So the client event source is like the Twitter for iPhone, Android, etc. They write logs out, and you read data from these client events. You filter them down to only impression events, and then you produce a thrift struct, which is called like the impression attributes thrift struct. Nowhere in this from producer block is there any aggregation logic being specified. Nowhere are you specifying that you're aggregating on tweet ID and producing count. There's no group by or sum happening over here at all. That's completely abstracted away for you by the SAR framework. So the on keys and produce block are enough to tell SAR to do the rest of the aggregation. So this is only doing event production. So it reduces the burden on the user by a lot. So let's see now things what you want to do. So your first example of your SAR job only was aggregating on tweet ID. Your product manager comes back to you and says, hey, I actually want to aggregate on client application ID as well. So I know which client application at Twitter is doing very well. So you need to evolve your schema. In SAR, evolving your schema is as simple as adding a new aggregation template. All you did was add tweet ID, client application ID, and extract the client field from your log source itself. And you deploy your SAR job. It'll automatically update your Hadoop job, your Storm job, your query service, your data schemas, your data integrity checks, all of the above, essentially. So it provides very easy schema evolution for you. Now, you've evolved your new schema. What about all the data that you computed in the V1 version of your product? Backfill is extremely easy to install. You just specify SAR Backfill, you give it a start timestamp and an end timestamp, and it'll start running. The cool thing is the backfill runs in parallel to your production job. So your production job continues to run, aggregating data as we go forward. And your backfill starts from whatever the start time you had and just comes in and starts filling in the data for you automatically. So it doesn't interrupt your production process at all. So this is useful for repairing historical data as well. Now, say in your first example of your product, you were only aggregating on daily aggregates. Your product manager also wants to know what is your all-time aggregates, or minutely aggregates, or hourly aggregates. So for SAR, it's as simple as specifying a simple configuration file where you specify your width, and then this is like a pistachio configuration file that you write, and then the SAR tool, which is written inside Python, parses this pistachio configuration, and then pipes that and like parses all of that through your SAR job itself. You don't have to aggregate on a new granularity. You don't need to round your timestamp down to an all-time timestamp or round it down to the daily timestamp. You don't have to write any of that logic in. You just specify this much and deploy your SAR job, and we take care of everything else for you. Similarly, so that's yeah, similarly, if you want to compute new metrics, so you've been computing only counts so far. Now, if you want to compute uniques, all you do is you enter unique user IDs. So far, we've been computing total number of views. So if a single user, if I see person X's tweet 3 times, that would count as 3 separate counts. But if I want to actually compute the number of unique users who have seen that tweet, then I want to add a new metric in there. Say I didn't realize that in the version 1 of my product. Version 2, I realized this. It's just adding a new metric in there. And we have a host of inbuilt metrics inside SAR, like counts, uniques, means, et cetera, et cetera. You can add new metrics very easily. It's just pluggable. Like the user can easily add a new metric in there if the user wants. So far, we'd only been persisting data to Manhattan, which is a key value data store. So you now want to persist data to a relational database like MySQL as well. That's, again, as simple as a simple configuration change for you. And you redeploy your job. And then it takes care of everything for you. It'll set up your MySQL tables and stuff for you automatically. And then the last thing is it provides an end-to-end service infrastructure with a single command. So all you type, the user has to type, is the word SAR deploy, like these 2 words. That launches your Hadoop jobs for you, your Storm jobs, your query service. Your Hadoop job doesn't write data directly into key value dish, writes it out into HDFS. This launches these loader processes to load the data from HDFS into a key value data store. It launches loader process to load these into your MySQL or Vertica database. We run on Mesos, so it generates Mesos configs for all of these as well. It'll generate alerts for you, observability for you, it'll create your tables and views for you. It'll also generate your data regression checks for you. So all of that is done by a single command, SAR deploy. And that's like the SAR tool, which is written in Python for us. So this is kind of what the bird's eye view of the SAR pipeline looks like. So you have HDFS log data, which is read in by the scalding job, which is running in batch. You have real-time events data that is coming in through Kafka streams that is being read in by a Storm job in real time. So your scalding job can write out data into a key value data store like Manhattan or into Vertica and MySQL. Real time can write data out into Manhattan as well. The summing bit query service layer merges the data from the batch and the real time and then surfaces that to a dashboard up there. And so you get a time series out of this. I think I'm kind of like out of time now, but I might have to stop here. But I can take any questions that you guys have. Thank you.